Swayam Prabha. Digital India. Educated India.
We have derived the linear momentum balance and then we are proceeding towards the Navier-Stokes equation. To understand the surface forces on the right hand side, we went to solid mechanics, understood stress, came back to fluid mechanics, understood total stress, and then we had completed the differential linear momentum balance, and then we realized that the viscous stress tensor components are unknowns. They ought to be related to velocity gradients. To understand velocity gradients, we need to understand displacement gradients. So, we went forward through this double headed arrow to solid mechanics, discussed about strain, and then now we are coming back to fluid mechanics to discuss about strain rate. Okay, that is where we are. In terms of our journey to the Navier-Stokes, we derived the differential form of the linear momentum balance with the viscous stresses on the right hand side. They need to be related to the velocity gradients. To understand velocity gradients, we first understood displacement gradient by taking a diversion to solid mechanics, and then we discussed these two blocks: strain, displacement gradient, strain tensor, rotation tensor, etc. Now, we are going to analogously discuss these two blocks for fluid mechanics. The highlighted two blocks are going to be discussed now. Okay, what is the outline? We have discussed difference between solids and fluids after our first visit to solid mechanics. When we came back to fluid mechanics after our first visit to solid mechanics, we discussed difference between solids and fluids. So, once again now we are coming back to fluid mechanics. So, we will discuss the difference between solids and fluids. It will be a revision, but we will highlight one particular aspect there. The topics which are going to follow are analogous to what we discussed under strain when we discussed solid mechanics. There we discussed deformation, normal and shear strain. Here we are going to discuss rate of deformation, normal and shear strain rate. There we discussed displacement gradient tensor. Here we are going to discuss velocity gradient tensor. Then we related the strain and displacement gradient. Here we are going to relate strain rate and velocity gradient. And there we expressed the displacement gradient tensor as sum of strain tensor and rotation tensor. Analogously, here we are going to express the velocity gradient tensor as sum of strain rate tensor and rotation rate tensor. So, these four topics are almost analogous to what we discussed for strain in solid mechanics. Let us start with the comparison of solids and fluids. We discussed the difference between solids and fluids under two categories. First, set of characteristics for which we know the difference between solids and fluids, that is what is shown here. We discussed in terms of distance between adjacent molecules, molecular arrangement, strength of molecular interaction, ability to conform to shape of container, capacity to expand without limit, and able to exhibit a free surface. So, these differences are all known to us. Then we went on to discuss the difference between solids and fluids, which is from a mechanics point of view, and that is this slide about. So, when we apply a tangential force to a solid, it starts deforming and deform until the internal stresses balance the external applied tangential force, and then it stops deforming, and that is what is shown here, an undeformed state and a deformed state. So, it goes from one equilibrium state to another equilibrium state, and then it stops deforming, and so solids can resist shear stress under static condition, and that is what is shown here, d c initial state, d dash c dash the final state. And if you remove the tangential force, the solid goes back to its original state. Now, if you do the same, if you apply a tangential force for a fluid as shown on the right hand side, it starts deforming, but now it continues to deform as long as you apply the tangential force, and that is what is shown here. D C are the points at some time t. As long as you apply, D moves to D dash, D double dash, C moves to C dash, C double dash. So, it continues to deform as long as you apply the tangential force. And now, if you take out the tangential force, it just retains the final shape as such. So, that is why we say fluids flow. So, now what is the implication? Because of this, fluids cannot resist shear stress under static condition. Even if you apply a very small tangential force, they start moving. Okay. So, fluids cannot resist shear stress however small it is under static condition, they immediately start flowing. Okay. Now, we also discussed the difference between solids and fluids using this coaxial cylinder arrangement. If you have a solid between the two cylinders and then try to rotate the inner cylinder, then the force required to rotate depends on how far the solid is deformed from an initial state. Okay. So, there is some initial state, and more you deform from the initial state, more the force is required. That is the case of solids, that is what happens in the case of solids. But in the case of fluid, what happens? If you fill a fluid between the two cylinder, now if you the force required to rotate the inner cylinder will now depend on how fast you rotate the cylinder. So, it depends on the rate of deformation. Okay. So, in the first case, in the case of solids, it depended on how far it is deformed, which means depends on deformation, the force depends on deformation. In the case of fluids, it depends on how fast you rotate the cylinder. In other words, the force required to rotate the inner cylinder depends on the rate of deformation. Okay. That is the key difference between solids and fluids, which are going to take as a basis for further discussion. Okay. We also saw an animation to show that fluids deform continuously. This is a flow between two parallel plates. The bottom plate is fixed, the top plate is set to motion at a constant velocity V p, and the velocity profile is linear. We have come across this several times. We identify a region of fluid, and then if you focus on that region of fluid, we can easily see that it continuously deforms. As long as the plate is moving, this region continuously deforms, and that is what we say that fluids deform continuously. Okay. So, the animation shows that this region continuously deforms. Okay. Of course, it replays back, but otherwise it deforms continuously. Okay. Now, this table highlights the differences from a mechanics point of view, which is of interest, which is of present interest to us. What are the differences? Response to shear stress. The key difference is that solids resist deformation, fluids resist rate of deformation, as we have seen, the cylinder example is the best example to understand this. On one case force depends on deformation, other case the force depends on rate of deformation, and we already discussed this earlier, ability to resist small tensile stress and compressibility. So, now let us summarize all the differences between solids and fluids. Solids resist shear stress under static condition, fluids cannot resist shear stress under static condition. Okay. Even for a very small shear stress, they cannot resist shear stress under static condition. Solids reach an equilibrium stage and stop deforming, fluids deform continuously, and so we say fluid flows. When the tangential force is removed, solids regain original shape, fluids do not return to their prior shape. Okay. Now, the major difference which is of importance to us for the present discussion is that the case of solids force depends on deformation, for the case of fluids force depends on rate of deformation. When we discussed stress for solids and then when we came back to fluids to discuss about total stress, we took lead from the first difference, and then we said fluids under static condition have some stress, when they flow they have additional stress and so on. Now, the difference which is of relevance to us is the last difference, and that is why this has been highlighted. In the earlier difference, the first difference was highlighted. Now, the last difference is highlighted, and we are going to take lead from this difference which says force depends on deformation for solids, force depends on rate of deformation for fluids. Now, based on this difference, we can intuitively write this table. What is that? For the case of solids it is deformation, for the case of fluids it is rate of deformation, and for solids it was translation, rotation, normal strain, shear strain. We just all now has to be discussed in terms of rate. So, we have translation rate, rotation rate, normal strain rate, shear strain rate. In the case of solids we had displacement field, displacement gradient. Now, in the case of fluids we will be having velocity field and then velocity gradient, and then we related the normal strain to the displacement gradient. Now, we are going to relate the normal strain rate to the velocity gradient. So, of course, we are going to discuss in further slides in detail about all this, but now based on the fact that force depends on deformation for solids and force depends on rate of deformation for fluids, we can come up with this table. Okay. Now, the way in which we are going to discuss the order of topics are all going to be analogous to what we discussed for strain under solid mechanics. So, some will be recall slides and other will be new slides for fluids. So, this is the recall slide where we defined normal strain and then shear strain. For normal strain it is change in length by original length. At a point we take a small line element along direction n, and the change in length by original length gives a normal strain. For the case of shear strain, we take two perpendicular line elements and then look at the change in angle between the initial state, which is pi by 2 radians, and the final state. Okay. Of course, this also we consider at a point and then two very small line segments which are perpendicular to each other. And a normal strain greater than 0 tells increase in length, less than 0 tells decrease in length, and if the shear strain is greater than 0, which indicates that the two lines have come closer to each other, which means there is a decrease in angle between them. If the shear strain is less than 0, then there is an increase in angle between them. Now, we will analogously introduce two measures of rate of deformation. Earlier it was two measures of deformation. When we discussed solid mechanics, we said there could be change in length, change in angle, and they are quantified in terms of normal strain, shear strain. Similarly, here for the case of fluids, we are going to discuss normal strain rate and shear strain rate, and this slide is for normal strain rate. Okay. So, how do we define normal strain rate? Earlier we have seen strain to be defined as change in length of line element. Now, it is rate of change in length of line element, of course normalized by the length. Okay. So, rate of change in length of line element is the normal strain rate. How do you express this formally? Okay. Now, this part of the definition is same as normal strain, which tells about change in length by original length. Now, we need to express in terms of rate of change of length. So, numerator tells change in length, divide by delta t gives rate of change in length, of course per original length. And now, we have two limits. The first limit is, as we have seen already, at a point we consider a small line element, that is why delta s tends to 0, and now we are divided by delta t, and the rate is defined as in the limit of delta t tending to 0. So, that is why you have another limit here, which tells delta t tending to 0. So, one limit makes the definition of normal strain rate valid at a point, that is why delta s tending to 0. Other limit makes the definition of normal strain rate instantaneous. This animation shows a rectangular element, and let us see what happens. If you focus on the line element AD, its length keeps increasing with respect to time. If you focus on the line element AB, its length keeps decreasing with time. So, this is what we mean by normal strain rate. In one case, of course, it is greater than 0, which means length increases with time. That is happening for line element along x axis. If you focus on line element along y axis, epsilon n dot, that its length decreases with time, and hence the normal strain rate is less than 0. Okay. So, this is a simple animation. Earlier when we were discussing solid mechanics, we were discussing a line element, initial length and then final length, but now we are interested in what is the rate of change of that length, of course normalized by the instantaneous length. Okay. So, same significance, but now it is with respect to time, okay. And that is what you see here. The length of line segment AD keeps increasing, length of line segment AB keeps decreasing. Okay. So, now let us define shear strain rate. How do you define? Earlier we said change in angle between two line elements. Now, it is rate of change in angle between two line elements. Okay. So, let us see how do you formally define the shear strain rate. Okay. So, the terms within bracket are the same what we have seen earlier for the definition of shear strain, okay. And now we are interested in the rate of change of that. So, divide by delta t and then delta t tending to 0. and once again we have two limits here. The first limit tells that at a point we consider two line elements which are perpendicular to each other. So, that makes the definition of the shear strain rate valid at a particular point, and we have another limit delta t, tending to 0. So, that makes the definition of shear strain rate valid at every instant of time. Okay. We always, in the case of solid mechanics, we need a definition which is valid at every point, but now we need a definition which is valid at every point and every instant of time. Okay. And let us look at this animation where initially the angle BAD was 90 degrees, and now the sides, the angle between AB and AD decreases, they come closer to each other, and the rate at which this angle changes is what we mean by shear strain rate. Okay. I like to mention that the way in which you understand shear strain rate is that we consider two line elements, let us say at some time t and some other time t plus delta t, let us say the two line elements become like this, they come closer to each other, and now the rate of change of angle is the shear strain rate. Okay. What does that mean? Pi by 2, initial angle was pi by 2 and then final angle was this, whatever angle between these two line elements, and the rate at which this change happens in the limit of delta t tending to 0 is the shear strain rate. Okay. Alternatively, it is a rate at which this angle plus this angle changes with respect to time. Okay. If you call this as beta, if you call this as alpha, then rate at which alpha plus beta changes with time is also shear strain rate, either way of looking at it. Okay. Okay. And remember, always it is the change in angle per unit time, and the angle at time t is always pi by 2. Okay. So, in this case the shear strain rate strictly applies only to the initial time instant, not as it progresses. Okay. Of course, if the shear strain rate is greater than 0, which means that the two lines have come closer towards each other, there is a decrease in angle between them with respect to time. Okay. And if the shear strain rate is less than 0, then the two lines have gone away from each other, which means there is an increase in angle between them with respect to time. Okay. Whatever we discussed for solids under static condition, now we are discussing as a rate.